So we will talk about numerical solutions for first order ODEs, and we mainly will talk two different strategies. One is the one-step numerical solution, and the other is the multi-step numerical solution. So we will start with the one-step numerical solution. Numerical solution for ODEs, or you can say first order ODEs with the initial value problem. And we will talk about one-step method. And this one-step method is basically use the values of the current step to estimate the following step function. So it's use of values from the current step for estimating next value of the function. And this will give us a range or a series of range quota formulas. So it's range quota formulas. And for this one-step method, the base of the one-step method is the Taylor series. So the base of this method is Taylor expansion. Okay, and for this Taylor expansion, you know that Yx plus h, which h is the step size, will be equals to Yx plus hy prime x plus h squared over 2 y prime double prime x plus h cubed divided by 6 y triple prime x plus dot dot dot. So that is the Taylor expansions, and that is the base for the one-step method. The h, we can call it normalized step size. Okay, so it's normalized step size. And if we let the y prime equals to f with as function of xy, y double prime will be equals to f prime, right? So y triple prime will be f double prime. So you can rewrite these equations by x plus h using function f. So y x plus h will be equals to y plus hf plus h squared divided by 2f prime plus h cubed divided by 6 f double prime plus dot dot dot. And you can rewrite this equation. So this is a continuous form equation. You can rewrite this as a discrete form, or you can write in a discrete notation. Okay, and we know that the x, if that is at step n, the n step will be xn, and we know this h is normalized step size will be equals to the next step minus the current step, the difference between two steps. So you can rewrite this as yn plus 1, that is equals to yn at current step plus hfn plus h squared divided by 2 fn prime plus h cubed divided by 6 fn double prime. So this is discrete notations to represent the Taylor series. And this one-step method is based on this form, and really depending on how many terms we keep or how many terms we truncate, we will generate different methods such as Euler's method or modified Euler's method, etc. So first we will start with Euler's method, which is the simplest one-step method numerical solution for first order ODEs. Okay, we will start with Euler's method. So Euler's method for first order ODE. And we can also call this Euler's method as the first order range quota. Range quota. Okay. So this is the simplest, as I mentioned, this is the simplest one-step method. One-step method. And how we write this Euler's method, which using our discrete notation, yn plus 1 will be equals to yn plus hfn. So we only keep the term of hfn and truncate all the higher term of h, and that is the Euler's method. So here there are some definitions regarding the arrow of this numerical solution. One term is called truncation arrow. And the truncation arrow, we can use tau to represent. So at step n, the tau n will be equals to yn plus 1 minus yn minus hf fn, which will be xn yn, right? And what we left will be h squared over 2 fn prime plus h cubed divided by 6 fn double prime plus dot dot dot. So that is our truncation arrow. And the biggest term of the h will be the accuracy. We can rewrite this as OH squared. So the truncation arrow is at the order of h squared. And this is also referred to local arrow at step n. We can use delta to represent. So at step n, the truncation arrow, which is also called local arrow delta, is as the order of h squared. There is also another term to represent the arrow. It's called global arrow. The global arrow, which is related to the total arrow expected by this computational numerical method. So it's related to the total arrow expected by such method. So here we were talking about is the Euler's method. And how about the total arrow? So for each step, the truncation arrow is OH squared, and we know that what is the total step of this process. So the number of steps, or you can also say the number of iterations, is 1 over h. Our h is the normalized step size. And how many steps in total during this process will be 1 over h. And we know that the local arrow is OH squared. So the global arrow will be use global arrow will be equals to, or estimate OH squared divided by H will be equals to OH. So the global arrow is as the order of H. The local arrow is as the order of H squared. And this kind of arrow analysis will help us to decide later what is the step size when we choose different numerical solutions.